Hey everyone, I'm back and today I would like to read this article with you. Fix a top cause of slow queries in PostgreSQL. No slow query log needed. This article was written by Eric Fritz, so let's go read it together. If you have followed our PostgreSQL series, you have seen that slowness in your database can sometimes be hard to diagnose. I didn't read the entire series, but if this article is good, for sure I'll bring more stuff from that series into the channel. And yeah, it's hard to diagnose, and sometimes you don't even know that the problem is in the database because you can receive the feedback of the problem based on observability platform that will inform you that a specific endpoint is slow and you are not sure if the problem is in the database or is something else. Sometimes it could be even a complaint directly from the customer, but once you know the problem is in the database, it's not clear as well. There is a couple of problems that are easier to figure out that it's a problem not exactly with the database, but maybe by the number of queries, like in the n+1 queries problem. If you don't know what is it, I left a article in the description you can check out, but basically it's a problem where, let's suppose you wanna select a item from the table and you retrieve 10 items, but then you want to join and select information from another table that is associated with that table that you are selecting. And if you don't implement the joins properly, this problem is very common with frameworks, database frameworks. You may doing one extra query for each one of the rows that you are retrieving. That's the name of the n+1 problem, and then that will put a lot of pressure into the database, and it's not a problem of how you are configuring your schemas and your database, but how the database is being used by the application. But some issues are obvious. At Render, we enable millions of developers to effortlessly deploy and scale full-stack applications. Render's managed PostgreSQL lets you connect any web app to a database in minutes. Given all the developers we support, we notice trends in what developers find challenging. One specific issue with PostgreSQL comes to mind. We might even call it the top most fixable cause of slow queries. Thank you for that title, because I will use it as a clickbait for the title of this video. Sorry about that, guys. Can you guess what is it? Read on and help reverse the trend. Spot the problem. A privacy-aware blog. Before we explain the problem, let's see if you can find it. Let's consider a scenario where we are designing a schema for a blog that respects users' privacy. In this app, users can create accounts, write articles, leave comments on articles. As part of the privacy guarantees, a user can delete any articles they write and can delete their account. When a user deletes their account, all their articles are also deleted. Their comments remain, but are displayed as written by a deleted user. To store data for this app, we create the following database schema. Create table users with ID, name, email, and created at columns. The ID is a primary key, the name and email are text, and the email are a unique, and the created at is a timestamp with time zone, and it is not null. And the default value is the response of the function now, the return of the function now. Create table articles. Similar to the other one, we got the ID, which is a serial primary key. The title and content are text. The author ID is an integer, is not null, and it's a foreign key of the users table to the ID column, and have this property of on delete cascade. So every time we delete a user, every articles created by that user will be deleted together. And as well, the created at field, which is a timestamp with time zone, not null, default now. Create table comments. ID, serial primary key, content, it's a text, not null. Author ID references the user's ID, and the article ID references the articles table. The difference is for the author ID, when the user is deleted, we are actually setting this value to null to fulfill that requirements of when a user is deleted, the comments must remain. But with the articles, we have the property of deleting on cascade. So every time an article is deleted, all the comments associated with that article will be deleted and the created at, the same as the previous one. This schema reflects our requirements. The users table stores information about registered users. 2. The articles table stores the title and text of an article and reference the author. The foreign key is defined with an delete cascade constraint. This constraint deletes all articles associated with a user if that user is deleted. 3. The comments table stores the text of each comment as well as reference to the author and the article. The foreign key to the article has a non-delete cascade constraint. This constraint deletes all comments associated with an article if that article is deleted. The foreign key to the author has onDelete set null constraint. This constraint sets the author to null if the authoring user is deleted. Where is the problem? Hint number 1. PostgreSQL auto creates some indexes. If you are thinking about missing indexes, you are on the right track, but which indexes? As a hint, let's first talk about what is not missing. Okay, I recommend you to stop the video and try to think about what index may be missing, but that depends on how these tables are being used, how are they being, the search on this table is being executed. With this extra information, it's hard to tell. Let's move on. Whenever you specify a primary key or a unique constraint, Postgres automatically creates a B-tree index on the constraint values. These B-trees indexes let Postgres quickly look up whether a value already exists in a given column, which lets Postgres reinforce uniqueness. I'll get the opportunity to talk about the B-trees because the B-tree data structure is a tree data structure, but different from a regular binary search tree. For example, here we can have many different nodes connected to a specific node, and inside of one node we can have multiple values. And this is interesting for databases, because with databases we can't just load the entire data from the disk into the memory. We can't do that. We don't have enough memory to do that in most of the cases. So we need a data structure that allows us to only load parts, chunks of the data, and search into these chunks. But the problem with binary trees, for example, is that a binary tree has a bigger height than a B-tree, for example, because with a binary trees we only can have one value per node and two children. And this is important because with the database we don't want to do multiple calls to the disk. We want to get a chunk of information, search into that chunk of information, and later we can decide that the information is not there and go after more chunks of data. But it can't be like, give me one node, give me one node, give me one node, like we do with a binary search tree. And this is why the B-trees are used in file systems and databases, because of this property of being able to store multiple information into a same node. And this allows to retrieve information in chunks but not require consecutive access into the database. Oh, give me this node, give me this node, give me this node. I may explain that in a wrong way or imprecise way. That is the main idea. I left a video in the description that explains exactly how a B-tree works. The video is from the spamming tree channel. It's an awesome animation, and we can visualize how inserts, deletes, and how that data structure can remain balanced. That is another attribute that is important in the context of file system in databases. These B-trees indexes let Postgres quick look up whether a value already exists in a given column, which lets Postgres enforce uniqueness. This means in our blog schema, Postgres creates indexes for the primary keys of each table, as well as the unique constraint on the user's email. We can confirm this by running /d and the name of the table in a PSQL shell. Here we go. We only have, in fact, the index for the primary keys and for the unique constraints. Don't you have the indexes for foreign keys? Even though Postgres creates this index for its own use, it will use these B-trees to boost queries you write to. In other words, if you do equally and range comparisons against any unique column, you can be assured that Postgres has created the index to make that query efficient. I still don't know where is the problem to this point, but let's move on. Hint 2. Let's run a simulation. To help us better understand this situation, we can simulate it. Let's set up a demo of our blog scenario and observe its performance. You can download the code and run the simulation yourself. Maybe you can do that later. First, let's create test data that include 1,000 users, 25,000 articles, about 13 million comments, randomly distributed among articles. Now, we will delete a user by its primary key. Let's examine the query plan for this deletion. Here is the query plan. Delete on users. It will do an index scan using the user's P key on the users table. The planning time is less than 1 second, pretty fast. And then it will trigger the constraint to delete all the articles associated with that user, and then trigger the constraint to delete all the comments for each one of the articles that are being deleted, and that will take about 18 seconds. That's a lot. And we have the number of calls. This is probably because we have 28 articles to delete, and so for each one of the articles it's going to delete all the comments. The entire query takes a staggering 19 seconds to execute. Why? At first glance, this query plan looks optimal. It uses an index scan to find the user by its primary key, which is very efficient and takes only 0.1 milliseconds. But this query takes a lot of time to process triggers for the foreign key constraints. Here we have a table with each one of the triggers and the execution time. The comments article one is the one that is taking 18 seconds. Remember, we specify on delete cascade constraints to fulfill our privacy guarantees. Triggers carry out the downstream deletions tied to a cascading constraint. In the simulations, the triggers delete rows in the articles and comments table that are tied to the deleted user. The large amount of time taken by these triggers indicate that PostgreSQL is likely performing full table scans to find the related rows. The bigger a table, the longer it will take to scan, so it makes sense that our comments table takes the longest. This is interesting because I thought that Postgres would already create index for the foreign keys, and we don't have transparency on how these triggers are being executed. So when we run this type of comment, I would expect to see that, because in a situation like this one, we are investigating the root cause of the slowness, and if you don't have that information, it's not easy to figure out what is going on. Answer: the missing index on foreign keys. Based on the simulation, we might have guessed the answer. The answer is that we are missing indexes on our foreign keys on one side of the relationship. As we saw earlier, Postgres automatically creates an index on the primary keys for each table: users ID, articles ID, and comments ID. In general, Postgres also automatically creates an index on one side of every foreign key relationships on the column in the reference table, but Postgres does not automatically create an index on the other side of the foreign key relationship on the column in the reference table. Got it. But the first part where Postgres automatically creates the index on one side of the foreign key relationship, if that column it's already a primary key, there is no difference because the primary keys already have the indexes. For example, author ID is referenced as a foreign key in the articles table. As a result of this schema declaration, if the ID column in the user's table, the reference table, did not already have an index, Postgres would automatically create that index. Within the articles table, Postgres will not automatically create an index on author ID. Though it seems like a sensible thing PostgreSQL could do, the missing index is what caused a performance problem. Yeah, that makes sense because we are deleting one user and then we are deleting 25 articles related to that user, and then for each one of the articles we need to do a full table scan, and then for each one of the articles we must delete all the comments, and for each one of the comments we are going to do that full table scan for each one of the articles actually. Yeah, that will take a lot, and this is why it's slow in the example, and as the table grows that problem will become greater and greater and greater. The Postgres could do that by default, of course with an option to not create an index for tuning purpose, but usually when we have these relationships is because we will need to query all this information, and if you don't have the index the performance will suck, and also in deleting as well. But I got curious because I never seen this type of problem before in any system that I have maintained. But I also use Django as a framework for most of the systems that I've working on in my career. And I got curious how Django deals with that, because with Django we don't create SQLs manually. We usually use the abstractions on top of the ORM, and I checked how Django deals with that, and looks like Django already creates the indexes for us. A database index is automatically created on the foreign key. You can disable this by setting db index to false. You may want to avoid the overhead of an index if you are creating a foreign key for consistent rather than joins, or if you will be creating an alternative index like a partial or multiple column index. That's perfect. I believe that this should be the default behavior of Postgres, but anyway, if you don't delete at all anything in the database, you will not have this problem. So do soft deletes as much as possible. Sometimes you can't just do soft deletes, you need to hard delete all the data in the database. When does the performance problem happen? Armed with this knowledge, we can now reason about all the situations where you may hit slow queries if you forget to add these foreign keys indexes. Situation 1. Common queries. In our blog application example, let's consider a fairly common operation, fetching all articles written by a particular user. Given a user, we want to find all articles associated with that user through the author ID foreign key relationship. Consider the following query. Select everything from articles where author ID equals to 123. Without an index on the author ID field in the articles table, this query would need to look at each row of the articles table and check each row's author's ID value against the desired user ID value. This operation becomes increasingly slow as the number of article grows, for sure, as you need to check each one of the articles. Yeah, it'll be pretty slow. Situation 2. Cascading deletes. What if we never need to make that particular query in our application? In that case, it means being savvy to skip creating the index on the foreign key. After all, maintaining an index you never use is pure overhead. It costs memory and disk to store, and it costs CPU cycles when inserting, updating, and deleting rows in the table. Well, not so fast. As we saw in our simulation, you must take care to create these indexes to support cascading delete operations. In our scenario, when we delete a user, PostgreSQL needs to find all the articles written by the user to propagate the deletion. But if you don't delete that record, you don't have the problem as well. Similarly, Postgres also needs to find all the comments on articles written by the author. Being the author the root of the aggregation, from a domain-driven design perspective, there is no way of accessing comments directly. You just see comments that are associated with an author. We just need to soft delete the author or the article, and boom, the comments are gone. You don't even need to remove that from the database. Of course, that will remain there. This will increase the disk usage, but we don't have these problems and all these complexities, and we can revert that operation. Fixing the simulation. To apply what we learned, let's fix the slow queries in our simulation. As a reminder, we simply deleted a user. This was the resulting very slow query plan. Here we have the same query plan that we have seen before, 19 seconds. To speed up this query, let's create indexes on the foreign key relationships. Create index articles author ID on articles author ID. So when searching all the articles associated with a specific user, we'll have an index to that. Create index comments author ID on comments author ID. Create index comments article ID on comments article ID. Note that we don't want to make these indexes unique because they represent many-to-one relationships. A single user can author multiple articles, and a single article can have multiple comments. These indexes will allow Postgres to efficiently 1. Find out articles by a specific author when querying articles or when deleting a user. 2. Find all comments by a specific author when querying comments or when deleting a user. 3. Find all comments for a specific article when querying comments or when deleting an article. With these new indexes in place, let's delete another user and inspect the query plan. The query plan is pretty similar, but right now the time is decreased a lot. Notice that the number of counts remain not the same, but as it is different records, we could have different number of articles and comments, but the relation of one to many remains here. But as we have the index, this is pretty faster than previously. The execution time less than 1 second. Awesome. The performance improvement is dramatic. The total execution time has dropped from 19 seconds to this less than 1 second, a 55-time improvement. In the updated query plan, the repeated table scans are replaced with repeated index scans, which efficiently jump to the range of relevant rows to delete. Let's break down the improvements. Yeah, that part of comments article relationship is where the bottleneck was and is completely fixed. This last improvement is particularly noteworthy. We see a 99.9% reduction in runtime, even though this particular delete operation deletes significantly more records than our previous deletion. The comments article ID foreign key constraint trigger is invoked 48 times in this deletion compared to 28 in the previous deletion. That's what I'm talking about. It's different users as it is randomly distributing the comments and the articles for each one of the users. Then we have the difference in the numbers. That's it. To have a better, fair comparison, we'd have a specific user, the same number of articles and comments, but we are more interested in the greatness of everything, not in specific metrics. Try it yourself. Proper indexing is critical if you want good database performance. As a rule of thumb, consider creating indexes on foreign key columns in referencing tables. Keep in mind that 1. Even if you don't query the relationships now, there is a strong possibility you or a teammate might add such a query in the future. Yeah, I quite agree that we should include these indexes by default because most of the time we need to do that. But this type of thinking in trying to predict the future is dangerous and can lead for unnecessary complexity in the software and things that you're probably not going to use. So for this specific case, I agree with that, but that advice you must follow carefully. 2. If you add an on-delete propagation constraint to a foreign key relationship, Postgres will query the relationship on delete. In this case, you absolutely need the index. Yeah, for sure. That's a good one. I didn't know about that. If I would write a database intensive application, like an enterprise application in other language, for example, Go, it's very common to not have a ORM. We just write plain queries. I probably would commit the same mistake as this article. Yeah, good to know this one. Which framework do you use to deal with databases? You do directly SQL queries, you use any other frameworks in other languages. In your framework, is this problem already solved like we saw with the Django one or not? Left the comments down below. Next, we encourage you to try running the simulation yourself. We have created a GitHub repo with scripts that make it easy to create a schema, generate demo data, and create the missing indexes. This was written by Eric Fritz. Check out Fix a Top Cause of Slow Queries in PostgreSQL. No slow query log needed. This was published in the render.com website, in the blog of the render.com. I imagine they are a company that can provide infrastructure or something similar. Check it out. I have downloaded the repository with all the scripts to reproduce with you the problem that you have seen in the article. I'm going to run a Postgres instance to do the test. Let's ensure that's properly working. Yeah, it is working. So we can now configure the environment variable that is needed by the script, which is this Postgres connection string. The script will rely on that environment variable to work and connect into the database. And we have a couple of different scripts locally. We have this one that can generate the data, this one to create the schema. That's probably the first one we need to run. The schema is created. In this other tab, I'm going to connect into the database. If we type \d, we can list all the relations in this database, so we can check that we already have the articles, the comments, and the users table. If we inspect, for example, the comments table, we can check that the only index that we have is for the primary key. The same we can do with the articles one. We only have indexes for the primary key. Next step, I'm going to generate the data. In this first attempt, I will not put too many data in the database. Here we can put how many users we would like. I will just use 10. The default one is 1000, and there is this default values which are to explain and show the problem. So this is why I'm decreasing the number. Let's just move on. We can type the percentage of the users that must be active, authors. We can choose how many articles each one of the authors must write. I'll just change it just to explain my point. And we have another questions that will be used to choose the number of data that will be inserted into the database. I just stick to the default ones and move on. We actually have 22,000 comments in the database. It's a lot of comments, but not as much as we needed to visualize that problem, because now I'm going to delete this script is going to delete a random user in the database. And it worked pretty fast because we have not that much data in the database. It took only 11 milliseconds. Now I'm going to generate the data again, but I'm going to use the default values. 1000 users. This will multiply a lot the number of articles and the comments. Let's see what happens. Invalid input, skip insertion. What is the problem? Okay, I need to choose between yes or no. Okay. Yes. Now we're going to have about 3 million comments in the database, and let's see how is this going to affect the performance of the delete operation. It's still running. In the meantime, we can talk about how this type of script is really useful. I don't know if there is some packages or frameworks that help construct this type of scripts, but that would be really useful to troubleshoot those type of issues. Usually when I get an issue in production, we wanna solve it as fast as possible. So if we have a tool like this one that can work with the tables that we have in a specific schema, that would be really useful. Or even though we don't have something ready to use, now with a generative AI, maybe you can use the LLMs to generate those sort of scripts for us, or at least we could have a base script and only use the AI to help us to translate the schema for each type of table, because maybe it's hard to make something that will work with any sort of relationship between these tables. But I don't know if we are in that spot yet, because my experience with AI is being a little bit painful until now. But that is something that it can help us. If it could speed up the generation of those types of scripts, would be nice, because usually we don't do this type of test because we are in a rush to try to solve the problem. Boom, now everything was created. The comments table is larger than before. If we try to delete a user, let's see how many time you take to do that. Finish it. It took half a minute, 21 seconds to delete the user. Now let's create the indexes. The indexes are created. If you inspect the table again, you see that we have an index for the author ID in the articles table, for example. Nice, really nice. If you check the comments table, we also have two new indexes, one for the article and the other one for the author. If you go back and delete a user, less than 1 second, the user is deleted immediately. Nice. This is the same thing as we have seen in the article, but was interesting to use those scripts because it gave me some idea on how I can use my local environment to reproduce problems that is happening in production. Definitely check it out, this repository, and try yourself running your machine and see how this affects the deletion. When we do this by interacting with a problem, we are using one more sense. So we can read, you can listen to, but when we actually type and see the problem occurring, this will help you to memorize and not forget that this problem exists, and allow you to understand and to get this knowledge in a better way. That's it, guys, for today's video. We have read this article together, learning something new. If you have any comment or feedback, feel free to left your comment in the comment sections below. Thank you for attention and see you next video. Bye.
Yo, you got slow queries, yeah, that's tracking you down, let's fix it now. Index is messing, that's a crime, full of table scans, waste one time, N+1 creeping through the ORMs, one by one, watch them jam, get it right, or watch your DB stall the night. Slow queries, fix that code, slow queries, fix that code. Tune it up, speed it up, optimize the load. Fallen keys, cascading deep, without an index, watch it weep. Delete one row, takes all night. Locking tables, left to right. Missing indexes on foreign keys, cascading deletes, bring DBs to their knees. Add those indexes, make it right, or watch performance drop from sight. Like, come on, subscribe if you feel this vibe. Fix your query.